Hey everyone, computer architecture students, and welcome to today's explainer. Look, if you're glancing at your syllabus right now and feeling, well, maybe a little bit overwhelmed by the sheer scale and complexity of the systems we'll be studying this semester, you are in exactly the right place. So, let's dive right in. Today, we're going to demystify the machine. We'll be taking a top-down zoom into computer architecture, giving you a complete high-level map of the territory so you know exactly how the big picture fits together before we get into the microscopic weeds.
Think of me as your guide today. Here's our roadmap. First, architecture versus organization. Second, computer structure and function. Third, inside multi-core computers. Fourth, the von Neumann blueprint. And finally, microprocessors to embedded systems. Let's get started.
Section 1. Architecture versus organization.
This is kind of the classic point of confusion for new students, and clearing it up forms the absolute essential baseline for everything else we're going to discuss. So, the crucial point is understanding the difference between these two terms, which honestly people frequently and mistakenly use interchangeably. Think of architecture, often called the instruction set architecture, as the programmer's blueprint. It includes the attributes of a system that are actually visible to a programmer. We're talking the instruction set, the data types, memory addressing, things that have a direct impact on the logical execution of a program. On the flip side, organization is the physical hardware construction that actually realizes that blueprint. It includes the hardware details that are totally transparent to the programmer, like control signals, memory technology, and internal wiring. For instance, whether a computer is designed to even have a multiply instruction, that's an architectural issue. How that instruction is physically implemented in the hardware, maybe by a dedicated lightning-fast multiply unit, or maybe by a slower mechanism that just loops addition over and over, well, that is an organizational issue.
And this brilliantly illustrates why that distinction matters so much, both historically and today. Let's look at the IBM System/370. This product line was introduced way back in 1970 and offered a whole family of computer models. Now, they all shared the exact same architecture, meaning the programmer's blueprint stayed absolutely constant. But they had completely different organizations, offering different speeds and price points. Because the architecture was identical across the board, a customer could buy a cheap, slow model and later upgrade to a much faster, way more expensive hardware organization without having to rewrite or abandon all their expensive software. It protected the software investment. Remarkably, with just a few enhancements, that exact same 1970 architecture still survives today in modern IBM mainframes.
Moving right along. Section 2. Computer structure and function.
Before we continue our top-down zoom to look at how a computer is actually built, we need to understand what it actually does. Despite the immense, almost incomprehensible complexity of modern machines, we're talking billions of parts here, their entire purpose boils down to 4 elegantly simple functions. First, data processing, manipulating data in a variety of fundamental ways. Second, data storage, and this means short-term memory while actively working on a task, as well as long-term storage in files. Third, data movement, shuttling data in and out via input/output peripherals or across the globe via data communications. And finally, control, the orchestration of all these individual parts so they work together seamlessly in response to programmed instructions. Literally every complex task your computer does is just a combination of these 4 basic functions.
Now, what's truly fascinating is how we can map those 4 conceptual functions directly to actual physical structural components. Let's look at a traditional single processor computer. The CPU, or central processing unit, handles the control and data processing functions. The main memory handles data storage, and the I/O handles data movement to the outside world. They all communicate across a system bus. If you zoom into the CPU itself, you'll see it actually has its own internal structure, an arithmetic and logic unit for the heavy lifting processing, internal registers for tiny amounts of immediate rapid-fire storage, and a control unit to manage the whole flow.
All right, time to zoom in further. Section 3, inside multi-core computers. We've just seen the traditional single processor view. Let's step it up to the next level and see how this builds into the modern multi-core reality. To navigate modern hardware without getting completely lost in the jargon, we need strict definitions right off the bat. A processor is the physical piece of silicon. It's the actual chip you can hold in your hand. A core, on the other hand, is an individual processing unit located on that processor chip. A core has its own ALU, control unit, and registers. So when you hear the term multi-core processor, it simply means a single physical piece of silicon that houses multiple independent processing units. This gives us a fascinating, nested, almost Russian doll type of hierarchy. Imagine how this is physically laid out in the real world. At the macro level, you have the motherboard holding main memory chips and I/O chips.
Plugged directly into a socket on that motherboard is the processor chip. Zoom into that processor chip and you find multiple cores, often sharing a larger pool of memory called an L3 cache. Finally, zoom into an individual core and you see its incredibly specific internal structure, instruction logic, its arithmetic and logic unit, and its very own smaller, lightning-fast L1 and L2 memory caches. It is literally an entire system nested inside another system. To really wrap your head around the sheer scale we're talking about today, check out this staggering real-world example. We're looking at the structural layout for the IBM Z13 mainframe processor chip. This single piece of silicon contains 3.99 billion transistors. No way, right? You can clearly see how the real estate is allocated here. 8 separate processing cores flanking the edges, with massive shared L3 caches taking up the center, right alongside memory controllers and I/O buses. It's practically a microscopic city, incredibly densely packed and engineered to absolute perfection.
Section 4. The von Neumann blueprints.
Okay, so now that we've zoomed all the way into microscopic billions of transistors, let's do a little narrative timeline twist. How on earth did we originally figure out this structural arrangement in the first place, long before microchips even existed? Meet the grandfather of all modern systems, the IAS computer, designed at the Princeton Institute for Advanced Studies starting in 1946. What you're seeing is the stored program concept. It outlines the exact structural divisions we literally just looked at in modern multi-core chips. A central processing unit containing an arithmetic logic unit, a program control unit, connected to memory, and input-output equipment. This architectural blueprint was so flawlessly conceived that virtually every computer you use today is still referred to as a von Neumann machine. The pure genius of this is best captured in John von Neumann's original 1945 proposal. He wrote, "Since the device is primarily a computer, it will have to perform the elementary operations of arithmetic. A central arithmetical part of the device will probably have to exist." Think about how profound that is. The guy was logically deducing and theorizing the absolute necessity of the arithmetic logic unit, the ALU, long before the physical microelectronic gates even existed to actually build a reliable one. He was literally drafting the blueprint for the future.
But just to anchor us in historical context for a second, the original specs for the IAS computer's memory were vastly different from what you're used to today. The entire blueprint called for just 4,096 storage locations or words, consisting of 40 binary digits each. To put that into perspective, that wouldn't even hold a fraction of a second of a blurry TikTok video. Yet the underlying architectural blueprint governing how that memory talks to the processor remains exactly the same.
Section 5. Microprocessors to embedded systems. From that single IAS blueprint, computing evolved rapidly, branching out into 2 radically different directions, scaling massively up and shrinking remarkably down. First, it scaled massively up in density and speed. Check out this mind-boggling contrast. The Intel 8086 microprocessor, introduced in 1978, which is basically the foundational ancestor of modern PC architecture, had 29,000 transistors. Fast forward a few decades to a modern 6-core Intel Core i7, and we're looking at 1.86 billion transistors. That is roughly 64,000 times as many transistors, operating 800 times faster, all packed into a physical package roughly the same size as the original. It's wild. But at the exact same time, computing shrank remarkably down into the physical world all around us. We have to draw a hard line here between general-purpose computers and embedded systems. General-purpose machines, like your laptop or a massive database server, are flexible. They're designed to run millions of different software applications. Embedded systems, however, are hidden computers housed within a larger product. They have fixed, highly specific functions. They run the Internet of Things, powering everything from the anti-lock brakes in your car to the smart thermostat in your hallway. Designing an embedded system forces a computer architect to work under severe, real-world constraints. Think about it. A pacemaker doesn't have a screen or a keyboard. It completely lacks a standard human interface. Instead, it's highly reactive, constantly reading the external environment through physical sensors. Because the software has a fixed function, efficiency is paramount. You have to aggressively optimize the processor's architecture for incredibly low power consumption, tiny physical dimensions, and low cost. Which brings us to our final thought for the day. Whether you spend your career designing architecture for a massive sprawling server farm or engineering a deeply embedded system for a microscopic medical device, you're still adapting the exact same fundamental von Neumann blueprint to meet different physical constraints. So, as embedded systems become even more deeply integrated into our physical world, sensing and reacting to everything we do, What will the next fundamental shift in computer architecture look like? Will we finally need a completely new blueprint? Keep that question in the back of your mind as we dive deeper into the hardware this semester. Thanks for letting me be your guide on this explainer, and I'll see you next time.